computer. And I'll say a very good evening to everybody, and thanks very much for joining us tonight. And Witt Reeve is going to give us a good talk about the magnetometer, how you set it up, how do you operate it, and what you're going to get out of it. And so I'm going to throw the mic over to Witt, and if everyone would mute their mics, that would make things run along a little bit smoother. So Witt, why don't you just move right along there and put up your slides.
All right, I'll put them up. Hopefully you're seeing a full screen of part 2.
Yes.
So this is the second part of a 3-part series that I'm going to be presenting. I did the introduction to geomagnetism last month, and this month we're going to do a description of the SAM-3 magnetometer itself, and then next month we'll go through some of the measurements that I've made with the unit here in Anchorage. So the SAM is an acronym for Simple Aurora Monitor, and it was originally designed by Karsten Hansky and Dirk Langenbach, both of them Germans. And I met up with them, I think in 2008, maybe it was late 2007. And Dirk, I have not been able to get a hold of him for several years now, but I correspond regularly with Karsten. And so if there's any problems that arise that I can't handle, I can usually depend on Karsten to help me with that. And but it turns out that there are very, very few problems with the SAM. So the original SAM was designed for radio amateurs. Both Karsten and Dirk were radio amateurs. And what they'd wanted to do is take advantage of enhanced VHF propagation whenever there was aurora. And aurora is almost 100% correlated with a geomagnetic disturbance. So they designed this device. It originally was a one-axis magnetometer, and but you could fairly easily add a second axis just by adding a second sensor. So in 2008, they decided to make it a 3-axis. It worked so well that they changed it or redesigned it for 3-axis, and that way it could be used for geomagnetism studies, both with X, Y, and Z axes. So with the SAM-3, you can build your own geomagnetic observatory. It's actually a pretty sophisticated kit. You can order it with 1, 2, or 3 axes, or that is 1, 2, or 3 sensors. It includes all the software that you need to operate and run the unit, the logging, charting, analysis software. It's great for both short-term and long-term observing. Now, it's usually used in a variometer mode, where you're really only looking at changes to the magnetic field. But it actually does work very well for long-term. I've been running the one in Anchorage here since early 2008. And so I have enough data now. I actually have a full solar cycle, and people have taken the data, my long-term data, and used it students have used it to write papers and things like that. I mentioned last time that the SAM-3 is part of the Space Weather Underground, or SWUG, and the University of Alaska Fairbanks is a big participant in SWUG, and the University of New Hampshire is even bigger yet. They have, I don't know, probably a dozen deployments scattered around the eastern part of the U.S., and they are using it for student outreach and things like that. NASA has also got involved. In fact, the lady that at NASA at Goddard that orders the SAMs from me. I first met her at the University of Alaska in Fairbanks. So it's a great project for student outreach, learning geomagnetism, operating your own observatory, and things like that. And I've uh, Karsten and Dirk asked me to uh, be the kind of the point guy for selling the units around the world, and I've shipped these things just about to every continent, including Antarctica and Pakistan and Reunion Island out in the Indian Ocean and all over the place. So it's a 12-volt DC box. You can run it off an AC adapter or you can run it off a battery. It's actually a pretty low current device, draws about maybe 100 milliamps or so. And you can operate it in a logging mode with a PC, or you can let it operate in a standalone mode. Now, it doesn't record any data. It doesn't collect data when it's in the standalone mode. It only has uh, the the indicator or the display that's shown here in the middle picture. It's a 4x20 LCD, and so you get the X component, the Y component, Z component, a K index indicator, the deviation, and the time. So the arrows over here on the right-hand side show you the trend. So you can see that the X and Y are more or less steady over the last 20 minutes or so, and but the Z-axis has decreased over the last 20 minutes. When you connect it to a PC, it uses the EIA 232 interface, the serial interface that is well known and well hated by just about everybody, but it really does work very well. And uh, so it is a pretty simple box as in terms of a user interface. And you've got 4 control buttons down here. Once you set this guy up, you forget about it, and it just sits there and collects data 24/7, 365 days a year. So when you buy the kit, which Don did, um, you get a pile of parts, and they're not sorted necessarily. There's about 100 parts there. They're all through hole, so just about anybody can solder them. There are 4 keyboard switches that are surface mount, but they're nice and big and actually pretty easy to handle for surface mount soldering. The software and all the documentation comes on a USB thumb drive. Used to come on a CD. And in fact, Don, your unit probably had a CD in it. The Both the construction manual and the software setup guide are probably out of date on your unit, and you can download the latest manuals from my website, or I can send you a link to Dropbox where you can download all the documentation that exists for the unit today. So what you have on your CD right now is out of date and does not include a lot. There's some application notes and additional documentation that I've written since
Okay,
then.
now I've passed that on. Roger, do you still have it?
Yes, I do. In fact, I just ran out of the room to go down and grab it from my shack. So I
Okay,
just pulled the hardware up here. Interesting. I'm not seeing any buttons like you're showing on it. Oh no, here we go. On a ribbon cable. Got it.
yeah, you ought to send Whit your details so he can send you this upgrade information.
Yeah, I'll send you a link to Dropbox, and you can download virtually everything that's available for the unit.
Okay.
Okay, got that, Roger?
Yep.
Good.
Yeah, so I actually haven't even powered this thing up. Derek actually built this thing and then handed it off to me. So, but I believe he did all the testing on it. We just haven't hooked up the sensors yet. I still have the sensors sitting here in a bag. Okay,
Great.
go
So
on.
you're actually getting pretty close to being able to deploy that. There is I do have an option that buyers can get a partially built kit, and what that is I build the PCBs and test them all together, so that and I test them with sensors in live sensors in my lab, and let it run overnight, maybe a couple days. And so that's an option that I found is fairly popular with some of the SWUG users. Now, the people in New Hampshire, they want the kits. They don't want anybody building anything for them. They're going to do it themselves. The people at the University of Alaska in Fairbanks, they buy kind of 50-50. They buy some kits that are already built up, and then the other ones, I guess they get their more experienced builders to put them together. But there's actually four components, three main components: a keyboard, a printed circuit board, the display, which is a liquid crystal display. It's on its own factory printed circuit board, and then the main controller, which is where all the work goes. So you don't need a lot of complicated or expensive tools. You do want to have a good quality soldering iron and solder. Uh, I recommend you do not use lead-free, although the University of Alaska, they insist that they use lead-free because they're real paranoid about the safety aspect of it. But I keep telling them, you get one free repair, and then the printed circuit board traces start to lift off. So I haven't been able to really get through to them about that. But all you need are some flush wire cutters, small pliers, and strippers, and a screwdriver and a nut driver set, a multimeter for measuring the voltages halfway through the construction, and so on. No blow torches, no Weller handgun type soldering irons. By the way, the one on the right is what I first had back in the 50s. And luckily, there was no surface mounted parts. All the resistors and capacitors were all big. And so that worked pretty good in those days, but won't work with the SAM kit now. Another thing that's actually pretty popular with the SWUG people is a learn to solder practice kit. So for a couple bucks, I send them a printed circuit board with some parts, a couple parts, and a battery, and they can practice on that printed circuit board. And so if they are going to destroy anything, they can destroy the learn to solder kit first before they destroy the SAM3. This is a picture of the completed printed circuit board. This is the main controller. And on the right shows all the parts that are mounted. You can see it's fairly compact, but not so compact that it's difficult to put together. And on the right is the bottom side of the printed circuit board. And the layout is actually pretty logical. The the different functions are kind of grouped together. You have your power supply, your real-time clock, your multiplexer for the three sensors, your 232 interface, and so on. So it's pretty well laid out, and I've been building these things, since 2008, and I haven't had a failure yet. This is the completed three completed printed circuit boards, the LCD on the upper right, the keyboard on the lower left, and then the main controller in the middle with the two cables that connect to the 232 interface and to the power. The ribbon cables connect the other printed circuit boards together. And on the first kits that I sold, I just gave the parts, and you had to actually assemble the ribbon cables in a vise, and that was kind of crude. I never liked it, so I started making them myself with a Panavise. There's two enclosures that have been available. The one on the right is the original enclosure. I never really liked it, but it was functional, and the main big problem with it was that you had to cut it, or the builder had to cut the holes, and boy, I saw some pictures of some that had been built, and the holes, it looked like they had that a rat had chewed through the enclosure. So what I did is I contacted a company called Box Enclosures. They're back in Illinois, and they have the box shown on the left. And what I do is I have them mill it out and drill all the holes so that all you have to do is uh, basically put the hardware, the fasteners together, and you have a nice clean installation. Plus, the box is big enough where you can put a Raspberry Pi inside of it. You could put any kind of maybe a small battery or some type of K-index bar graph or something like that. So it's actually a pretty nice setup. They're not cheap, but they do make a nice project out of it. The firmware, there's actually two firmware that come with the unit. You have the initialization firmware, which is preloaded on the processor, and that is used to do the calibration of like the K-index indicator, to test the 232 interface and all that kind of stuff. It completely tests every interface on that board. And then once you've got everything working, then you can install the operating system firmware. And you don't do that until you have everything working, because it's just flat not going to work at all with the operating system firmware on it if you haven't pre-tested it. So the processor then, or the MPU, comes with a bootloader preloaded on it, and so it's really easy to use this pick downloader down in here on the lower right, and you use that to load the operating system firmware on it once you're finished with the initialization. Now, if you for some reason you want to go back to the initialization firmware, you just run this pick downloader again, but you, instead of the SAM operating system file, you select the initialization file. And so you can go back and forth all you want on it. And one of the things that you do with the initialization firmware is you set the time and date. Now, once you've loaded the operating system firmware, the only way you can update the time and date if you need to is with the SAMView software. So I'm sorry, the SAM INI software. So that works with the operating system firmware and allows you to set time and date and other parameters as well. Now, when you're doing your initialization tests, one of the really important tests that you do is the RS-232 or the EIA-232 interface. And if that doesn't work, then you're not going to be able to log data or anything like that. So you use a simple terminal emulator like TeraTerm, PuTTY, or even HyperTerminal if you still have that. And you can use that then to test the 232 interface. So you need some extra software to make that one test. You don't need TeraTerm or PuTTY or whatever once you've loaded the operating system firmware on the system. Now, this is a block diagram, and this is simplified, but you have your main controller, the MPU here in the middle, and a multiplexer, a couple chips that do the multiplexing of the three sensors over here on the left-hand side, your voltage regulator. There is an individual dedicated voltage regulator for each sensor. So if you have three sensors, then you have these three voltage regulators. They output 5 volts out to the sensors. You have a real-time clock. You have a K-index indicator, and this is just an analog signal that has a 5-volt max scale, so that a K9 index would be 5 volts, a K0 index would be 0 volts, and it's linear in between. And you have to calibrate that. You don't need to calibrate it if you're never going to use the K index, but it's part of the initialization testing. You have your 232 port transceiver, an optical isolator for your if you're going to operate a transmitter nearby, and what that does is it stops measurement of the SAM until you unkey, and then it resumes measurements. And then you have an alarm that you can hook to a lamp or a buzzer or something like that. And this is for people that want to either go out and photograph the aurora, or maybe take advantage of radio propagation associated with it. So those are the interfaces that you have for external. There's two pluggable connectors on the SAM.
Quick question.
Oh, go ahead.
This is Roger. How close do we have to worry about amateur radio broadcasts?
Yeah, that's a good question, and I don't have an answer for you. I don't use that feature myself because I don't have any transmitters here. But I think that's something you're going to have to figure out experimentally. And I would say if you're operating a 1500-watt linear, you're going to have probably a problem no matter where you put your SAM3. But if you're low wattage, then maybe it could be closer. But I don't have a feel for that, unfortunately.
Okay, Paul, I think that you're thinking of moving the HF stuff to the building. Is that correct? Paul?
Sorry, I was muted. Yeah, that's correct. We're going to be moving it, so the putting it by the bunker will be far enough away.
Yeah, so that's going to be like 400 or 500 feet away from your 1500-watt amplifier.
Yeah, well, I mean, of course, you're talking about inside a metal building, and the antenna is going to be fairly directional. So unless we're pointing at it, it shouldn't get much there anyway.
Yeah, hopefully
Okay.
that's not going to be a problem for you. You definitely should look into using the voltage detector function on the push to talk. And if it's something that you're not using, for hours on end, this shouldn't be a problem for you. You'll definitely lose some measurements, but the SAM will just go back into normal operation once you unkey or are done, with your contacts or whatever you're doing.
Okay.
So
Go ahead. Thank you.
We'll have a fiber connection between the building and the bunker, and we could probably hook up something that would do the PTT same time that we're transmitting. So, but Roger and I can talk about that later.
Yep.
Okay. Yeah. So you have the X1 connector on the controller board is where you're going to be making all your connections like that. And it's pretty well explained in the documentation. The the push to talk is opto isolated, and it's a 12-volt type control. So you may have to have maybe an external relay or something like that between your actual PTT and the SAM, but it should be pretty easy to figure out. The other connector, the X2 connector, is a 10-pin connector. It requires or uses 3 pins per sensor. There's a 5-volt power going out to the sensor, the signal coming back, and then they use the power and signal use a common ground lead. So you have one of those sets of 3 for each X, Y, and Z sensor. And then there's also a temperature sensor connection on pin 10. Now, the temperature sensor is described in detail in the documentation, but I don't support it. And the reason I don't support it is because when you set the SAM for a real fast sampling rate, the temperature sensor does not keep up with it. So what it means is that the data file that you get, the text file with all the data, will have there will be timestamps that are skipped, and there won't be a temperature in there. And I didn't want people calling me up and telling me the damn thing didn't work. So I just say I don't support it. You can use it at your own risk, and here are the details for it. Uses the old Maxim or Dallas Semiconductor Maxim DS18B20 temperature sensor. It's a one-wire bus protocol device. It actually does work really well. It's just that if you're sampling too fast, you'll miss timestamps with temperature. But other than that, everything is operating normally. Over the years, I've been asked to build special applications, and like for a portable system, I built some up, and these had an internal recorder in them so that they could be taken out in the field and dropped off and operated off a battery and would actually record data. Without a data recorder hooked to that serial port, you're not going to get any data collection with the SAM3. It has to be connected to something on the serial port because that's where the data goes, is out on the serial port. So in the standalone mode, what you are using it for then is to get real-time data shown on the display. You got the data, the K-index, and the time on the LCD. You also have the alarm output so that you can operate this thing standalone without a connection to the PC. And then if you have a geomagnetic disturbance, then the alarm will go off. You'll have a light or a buzzer or a siren or something hooked to it, and that grab your camera or your VHF and start working with it there. Now, if you're wanting to collect data without an external recorder of some type, then you need to hook it to a PC. We supply the Windows software with it, and I'll talk a little bit more about that later. But all the software that you'll need is supplied with it. You can set the data sampling interval from 1 to 120 seconds, I believe. And usually, if you operate it at 1 second interval, you're collecting a a lot of data 24 hours a day. So what I do on mine is I set them for 10-second sampling interval. And I've also run them at 60 seconds or 1 minute interval. It seems that in the magnetosphere, nothing happens instantaneously. So 10 seconds seems to be a good compromise. 60 seconds, maybe you'll miss the rising edge of a sudden impulse or something like that. But it's up to you to set whatever you want. And you can run it with or without logging if you're hooked to a PC. Now, the Windows operating systems that the software works with and has been tested with is XP through Windows 10. Now, I'm operating Windows 11 right now for the last maybe month or so, several weeks in my lab. And It's working very well. The big problem, though, with all of Windows is having the correct driver for the USB to serial adapter that you're using to convert from the 232 interface to USB. Now, if you have a native 232 port on your computer, then you probably don't have to worry about that. But with Windows, as everybody knows that uses Windows, if you don't have the proper drivers, it's not going to work very well. When you install the software, you basically are just putting a bunch of files on the hard drive. There's no real installation in terms of going in and monkeying with the Windows registry, which is potentially a disaster on a lot of Windows boxes. There's no Linux or Mac software provided, but others have written Python code to collect data using Raspberry Pis, which are operating Linux and Mac. So there is a way around it if you hate Windows so much that you don't want to use that. If you need it, get a hold of me and I'll put you in touch with people that have written this code. Now, the first software that you're going to use with the SAM3 after you build it and install the operating system files is the SAM INI, or initialization software. And you can use this to set the date and time, although that already should have been set when you did the initialization with the original initialization firmware. You can change the output interval. It's shown here, set for 10 seconds. You have to specify a COM port in order for this to work. You can also set a sensor correction and offset for each of the X, Y, and Z sensors. Now, you typically don't mess with that, but there is some information in the construction manual, or the software setup guide, that gives you some guidance on how to do that. A lot of people think that you can use the SAM3 as a super well calibrated magnetometer, and that's not true. It's a variometer, and there's the sensors are too separate, temperature sensitive to operate in a calibrated mode for very long. So, but if you want to go ahead and do that, then the software does allow you to make adjustments for that. The K-index. Now, one thing about the K-index is that the manual goes into a lot of detail about how to set that, but it's not needed. You don't have to set it. You can use default values unless you're actually interested in having a K-index displayed on your magnetograms. So the values shown here are for in the neighborhood of maybe 40 to 50 degrees latitude, maybe closer to 40 degrees. I think you guys are at what, 43 degrees latitude down there. So the default values may work very well for you, but the manual tells you how to adjust them. Now, once you've got everything the SAM INI all done and everything's working, now you can load the SAM view. And SAM view is the one that gives you the magnetogram and allows you to collect data. So you can set things like the legend on your magnetogram. You can select what if you want to display K-index. You can set it to display or not display any of the X, Y, or Z. You can set the scale or auto scale for the Y-axis on the magnetogram. And so notice that there is a K-index table here on SAMView. Now, this is a different K-index table than shown with SAM INI. SAM INI loads this value into firmware on the controller. And that is what is displayed on the LCD. This one here is what is displayed in software on the magnetogram. And then once you've got those settings going, then you go to the press the logging button, and then you can set up the logging. Now, once you've got everything working, then you should see a magnetogram that might look something like this. This is actually up at Gakona. They're at 63.5 degrees magnetic latitude. So things are pretty active up there, as they are here in Anchorage at 62 degrees latitude. But what you'll see down there will probably be muted compared to what I see, but it'll still be a 24-hour display or chart, and it's broken into 3-hour synoptic periods. And the K index is based on the peak-to-peak change in a 3-hour period, 0 to 3, 0300, 0300 to 0600, and so on. So the K index is a universally loved index for magnetic field study. And just about every paper you'll ever read on it somehow or other refers to a K index. Now, if you're lucky, you might even see some ULF waves, which are these little variations. They used to be called micropulsations. And I'll talk about this more in greater detail next month. But you might even see little variations like that in your magnetogram. You typically set it for auto scale, and you can set it to display the color code for the X, Y, and Z axes, and it displays down here in the lower left time in coordinated universal time on the horizontal scale. You can turn on the K index if you want, or you can turn it off. You can adjust all of the text up here on the legend. So you have quite a bit of control with SamView. Now, there's another piece of software that comes with the unit called SamStat. And this is your K-index statistics, very similar to the Bartles diagram. And the nice thing about the Bartles diagram is that it's based on a 27-day rotation period of the sun. So you can collect your data and then use SamStat to display it. And if you stack these K-index charts on top of each other, you'll see, you probably will see activity that repeats every 27 days, plus or minus. And that's the rotation rate of the sun. So it's a pretty handy little piece of software. Sam Browser is another piece of software that comes with it. And what it is used for is when you use SamView to collect data, the data is saved as a .sam file. It's and you can then use Sam Browser to load a whole bunch of these files in and display them, and allows you to save them as a text file. So it's a nice another nice piece of software, but it's not needed for operation. This is for post processing of your data. Sam Convert is I'm sorry, I think I said incorrectly that the Sam browser converts your SAM files to text files, but the Sam Convert is the one that does that. That's another piece of software that's supplied with the unit when you buy it, and you can bulk convert your files. So it's those are more or less the main software that come with it, and they're all Windows based, and they all work very well. I've never ever had a crash or identified a bug in any of these. Now, the data format is actually really simple. The 232 serial port interface pumps out the data at a moderate speed, 9600 bits per second, and it puts it out as a text file so that it's really easy to read. It's in a tabular format. You have your date and your time, and then X, Y, and Z. And there's actually different delimiters used. There's a space delimiter between the date and time, a colon between the time and then the data itself, and then there's a comma delimiter for each of the three axes. So the data can be processed downstream really easy because it is simple text data. There's no binary data involved here. So let's see what else we got. The data files are saved as .txt files, so they're text files, and then all of the software that I showed previously, none of this alters that data. So in other words, you can monkey around all you want with SAMstat, SAMbrowser, SAMconvert. You'll never change any of the original data. And that was something that Karsten and Dirk were very careful about. They didn't want anybody to change the data. They wanted to be able to process it, but not change it. So that's good for archiving purposes. Now the sensors. You get 1, 2, or 3 with your order. I think the one that Don got had 3 sensors in it. They're 5 volt. They operate off of 5 volts DC. Their output is a pulse width modulated signal that's proportional to the magnetic flux density. And the range is plus or minus 50,000 nanotesla. So it fits very, very well with Earth's magnetic field, which, except for some places up near the magnetic poles, that range covers you very well. The resolution is really good, 1 or 2 nanotesla. They're very temperature sensitive. So that's why we recommend that you bury the sensors, and the deeper you can go, the better off you are, because they will drift. They have a negative temperature coefficient. They will drift with the temperature. And if you bury it only a foot below the ground, you'll be surprised at how quickly the ground heats up after the sun comes up with these. So you have to get them down very deep. Now, the original sensors were made in Great Britain by a company called Speak. And the old man, Speak, died, I think it was in 2000, when was that? 2011 or something like that. And or I'm sorry, 2017. And so the 4 terminal sensors that he made were no longer available. And there is a replacement that's a 3-pin. And my experience with it is that it's equivalent to the old Speak sensors. But you have the original Speak, the FGM3 type sensor, and they work very well. I can tell you that I've really, really abused these sensors in my lab when I was first getting started with the SAM, and I never was able to destroy one of them. I've never had one go bad on me. So hopefully yours is going to work for you for a long time. Now, what I do is I mount the sensor in a monkey cage, what I call a monkey cage, and then that monkey cage slips into a piece of PVC pipe that is actually buried in the ground. And you can see that there's filter capacitors right at the sensor, and these are actually glued in, and then I've coated them with epoxy. And so this is what I do. You can probably come up with a different scheme, but it seems to work pretty well for me.
Something I
sensor.
found is
What's
that
that?
something I found was 1/2 inch PVC. They fit perfectly in.
Yeah, and but let me caution you about that. The now I've never had this problem, but I've seen reports of people that have done that with the FGM3, and the heat dissipation is pretty small, but if there's no airspace around the sensor, then they may overheat. So that's just a caution. I've never had that problem, but I've always provided an air gap around them as shown here. So
Ah, okay, that's good to know. I didn't realize there was a heat problem there.
they only draw about 15 milliamps. And so they're not a high wattage device. They don't dissipate a lot of heat, but you'll notice that when you do bury these things, that it takes about 10 days for the soil to stabilize in the vicinity of the sensors. And that's because of the heat dissipation from even though it's pretty small, it's still enough to be measurable. And so you might want to watch that before you seal it up and put it in the ground. Let it run for, maybe a couple weeks and see what happens. And hopefully you're not going to have a problem with that. But
Actually, these monkey cages look like they'd be an interesting 3D printing project. So I might just go
exactly.
that route.
Exactly. And yeah, these were built before 3D printers. So and yeah, definitely I would have done it different today. But yeah, that's a good idea. You can print something up that'll work much better, a lot less work than these wooden jobs that I've got here. Now, the sensor fixture itself, I don't supply those, and the reason is because um, everybody has their own idea on how to do it. There's the One of the big problems is that they're fairly intensive. You have to cut all the pieces and glue them together and double glue them and all that kind of stuff. And by the time you do that, you can't afford it. So I didn't want to mess with that part of it. Anybody that has any kind of basic skills can build these up out of common ABS or PVC pipe. And in fact, the furniture PVC fittings work really well for this. And you can get them at the hardware store or order them online, all the parts and pieces, and then cut them yourself. But it is important that you thermally insulate the sensors. And a lot of the people that have bought the SAM have put them in a picnic cooler and put them in a closet in their bedroom, and actually have gotten fairly good results out of that. But if you're really serious about getting good, clean data day in, day out, then they really ought to be buried. This is just another view of this is actually a one axis type sensor, and using common 1.5 inch PVC, and for the monkey cage, and then 3/4 inch standpipe that goes from the buried portion up to the surface where there's a junction box and a connector and what have you for the cable that comes from the sensor itself. And this can be extended to a 3-axis very easily. Here's the one that I have here buried in Anchorage, and it's about maybe 5 feet long total. And the z-axis is down here at the very bottom. The x is right above it, about 6 inches or so, and the y is maybe 6 inches above that. Now, I think I mentioned the last time that it's a good idea to separate the sensors from each other by about 6 inches. And that's because if they get too close, they will lock into each other. and stop actually measuring the magnetic field. They're trying to measure each other, I guess, is what's happening. So keep them separated and make sure you test it very well before you commit it to the earth. Here's just another version of that sensor, our sensor fixture. This is made from furniture PVC pipe, and it. I used a 5-port T here, and so I have the Y and X at the same level, but they're separated by roughly 6 inches, and then the Z is pointed vertically, as shown here. Now, one of the things uh, you have to remember is that the sensors are orientation specific. So if the magnetic field surrounding the sensor increases, you want it to increase on the magnetogram. And that won't happen unless you have the pins or the axis of the sensor oriented correctly. And this is described in detail in the construction manual so that you can get those correctly. Now, this is an installation in Switzerland, and you can see he's got a junction box here and a standpipe down to the sensors that are down actually buried in your ground. And this is what he used to make that installation. So did it the easy way. But you can also do it the Armstrong way. And this is one of the systems that I installed initially here in Anchorage. And I buried it with a shovel and a local supply of dirt. And so there's a lot of ways to do the installation, the hard way and the easy ways. Now, one of the things about the sensors that sometimes with the cables you'll have crosstalk, and so the crosstalk coming from the cables will make one axis very noisy, or maybe all axes very noisy. So if you have that problem and aren't able to solve it using any of the techniques that are mentioned in the construction manual, then you can use this 422 interface, which is a balanced interface that uses the 485 type chips for transmission purposes. And this extends the sensor distance to, I don't know what the distance is. It's going to be at least 1 kilometer, maybe even more than that. And it's basically a 485 interface at the transmission side, and then it connects to the SAM sensors on the interface side. So, and it's power over twisted pair. So you're going to power the far end at the sensors with one of the pairs. And this is just a simplified diagram of how that works. So you have a 485 interface, and you're only using the one direction from the sensor to the controller. And that's each sensor, X, Y, and Z, uses one of the 4 pairs in a Cat5 cable. And then the 4th pair is used to supply 12 volts out to the individual voltage regulators for the sensors themselves. So this is a very simple setup, and I have printed circuit boards for this. If you need them, I can supply with printed circuit boards. There's no parts on them, but the setup works pretty well. And you can use Cat5 cable that's made for direct burial applications, that's shown here. This is what I use up at the HARP facility at Gakona. I use the buried twisted pair for a 422 interface. So that's pretty much brings me through to the end of part two, and I've shown some additional references here for you. I put these in the chat this time, so you should be able to download these. But there's an article that I wrote a few years ago on citing the sensors. And this was a case study that I did here in Anchorage. And it'll give you some insight into how far away you need to be from like automobiles and tools and things like that that could disturb the sensor readings. There's also an article on burial depth, and I go into the soil damping factors and a little bit of civil engineering there to give you some insight into how deep you should bury according to the different types of soil that you might have. There's the article on the 422 interface for mitigating crosstalk. There's an application note on using a serial data recorder. This is kind of out of date. I don't know if those recorders are still available or not. There's an article on calculating the ULF wave spectra from the magnetometer data. We'll talk about ULF waves a little bit on next month's installment, and construction manual software setup guide. I think you already have the links for those, but these whatever's on my website is going to be the latest available. There's a document and on the BEN1 box enclosure assembly. It's pretty detailed, but it's so simple that you don't even really need instructions for it. And then, of course, the tutorial that I mentioned the last time, which I highly recommend that you take a look at that to get some ideas on what you'll be seeing. So that's pretty much it, I think, for today. And open to questions if you have any questions.
Yeah, how far away without that 422 interface do you think you could get away with running like 22 80
Yeah,
okay,
and
go
that's
ahead.
I get that question pretty regularly, and of course, the answer is it depends. But in the installation I have here in Anchorage, I'm running 50 meters. And I'm using twisted pair. I did have some crosstalk problems. I was able to fix that by using a low pass filter, and which is described in the construction manual. So I would say that you could probably go beyond 60 meters, but you're going to have crosstalk problems unless you do something to mitigate that up front. For example, separate each of the cables physically when you bury them or lay them on the ground or whatever, so that the chance of crosstalk is minimized. So yeah, that's a tough question to answer.
Okay. And I already forgot my second question, so I'll let someone else get in there while I'm remembering what that was. Let's see. Oh, I saw in the construction manual it said that it didn't really matter if there were ferrous objects nearby as long as they weren't moving. Um, to So my biggest worry about our site is it's an old government site, and there are metal bits everywhere.
Right.
And so I'm just wondering how much of that may poison our results.
Yeah. When it's used as a variometer, it's probably not going to affect you very much, because you're looking for changes, and your local magnetic field is going to be distorted by the all these metallic objects that are in the ground or wherever they are. But since you're looking for variations, then I don't think that's going to be a big problem for you.
Okay.
Now I need to qualify that. If somebody buried a huge magnet in the ground, like a huge motor with permanent magnets in it, then yeah, you've got a problem there because that's going to distort it so much that even the variometer isn't going to give you good readings.
Okay, I hope to not have that problem, but yeah, we're going to be installing this near the bunker. But it sounds to me like, we can probably site it, within 20 meters of the bunker and away from the road, and that probably would work out.
Yeah, the every time a something drives by the where the sensors are, you're going to see that as a spike. Now, in my installation here in Anchorage, my sensors are roughly maybe not quite 10 meters from my driveway. When I drive up my driveway, I don't see any effect whatsoever. But if Federal Express drives their truck up my driveway, I see that as a spike. And if a grader comes down the road, maybe, 20 meters away, I might see that. But it's a transient, so it doesn't really affect anything long term for sure.
Yeah, we're probably talking maybe 20 to 30 meters away from the road.
I think you're going to be okay. What you should do is look at this article at the very first here, the sighting of the magnetometer sensors. That I think would give you some pretty good insight as to what I saw over the study period I did here in Anchorage, and where I compared a remote set of sensors to ones that were in my lab, and so that might give you some ideas on that'll help you out.
Okay.
Hey, Witt, it's Paul. Just a quick question about RF interference from amateur station. Is it is it frequency dependent somewhat? Like if I'm on 160 meters versus say 2 meters, is there a some differences between those two in terms of the impact?
Yeah, I don't know the answer to that. I probably should ask Karsten because his original application was the 2 meter or the VHF type setup, and I suspect that maybe he was getting interference from that, and so he built uh, that push to talk sensor in there for that purpose. Now, going down to HF, 160 meters, what's that, 3.5 megahertz or something like that? Um,
About
yeah,
one,
you're
about
getting,
1.9,
what's that?
1.9 megahertz.
1.9. Okay, yeah, but I must be thinking of uh,
Just about the
80
broadcast band.
meters then. But yeah, now at 1.9 megahertz, you're getting into the vicinity of the sensor operating frequency. Um, you're still maybe roughly 10 times the sensor operating frequency, but subharmonics could cause you a problem. So yeah, you're going to have to do so. I think you really need to do some experimentation because I don't really have any experience with that.
Yeah, now with some new hand bands that are like 350
Oh,
meters, which are really really low frequency. You're below the
yeah, those, hope we won't be doing that.
you know
Roger, if you would like, if you want to send the 422, couple of 422 boards
I
for
don't.
isolation, I can pick them up.
Yeah, let's let's try to keep it simple initially. And if we have a
Suits me.
problem,
Sure.
yeah,
But I'm saying if you run into that as a problem, just let me know, and I'll just pick them up for the club. No
Okay,
big
yeah,
deal.
that's fine.
No biggie.
And take a look at this document here, and they're really easy to build. That when I designed the printed circuit board for this application, I put in all kinds of different options, I guess you might call it, to test. And it turned out that the simplest setup was the one that worked and worked
Sure.
the best. So the printed circuit board has actually room for a lot of different components, but you only need the integrated circuit and a few resistors, and that's pretty much it, and the
Right.
connectors. So um, do take a look at that, and if you think you need them, then yeah, I'll be glad to send you a couple boards.
do you have the, I'm looking at your site. I'm wondering if you've got the, just the box available. Since we have the magnetometer, we have no box for it. Wondering if you have that sold separately.
Oh yeah, I do. Yeah, I do have the boxes and
Oh,
they're
there it is.
ready to
Yep.
ship.
Okay.
This is Adrian. I have a quick question regarding your sensor crosstalk. Has anyone tried individual sensor burial locations rather than having them all together in one unit as you've been sort of showing there?
I don't know of anybody that has done that. Because it'd be basically three times the work. But the crosstalk, there's actually two kinds of crosstalk, and this is discussed in the construction manual. There's the potential for crosstalk between the sensors themselves. So if you have the X and Y sensors too close to each other, then they're going to interfere with each other. There's the other type of crosstalk that you can have is in the cables. So you could certainly bury the individual sensors at separate locations with the cable going to it, and as long as those cables aren't close to each other, then you shouldn't have any crosstalk problem at all with either the sensor or the cable. But I don't know of anybody that's actually done that.
Okay, thank you.
Okay, if sounds like we've got a lot of good questions there. And I wanted to, if there's nothing else, I'd like to thank you so much for doing this for us, Witt. And this is really fascinating stuff you're working with there. I'm definitely interested in the K index, obviously, for Aurora and stuff like that. So I think that's a great feature to have on your system. And
Yeah, and I'm looking forward to next month and where we can actually look at some of the data.
mhm.
And but like I said, I'm at higher latitude than you guys are, but sometimes I wish that I was at lower latitudes so that I could look at the fine points in more detail because it's so busy up here magnetically that
Yeah.
I'm sometimes I'm afraid that I miss some of the small stuff. So you guys will be able to see that really good.
Oh, that's great. Well, thank you very much. And that'll make a lot of difference for us. I'm hoping maybe there's some way that we can tie this into our website so that we could have like real time um, displays on our website. So
Well,
uh,
what I do is I have SamView set up to not only save the data itself as a text file and .sam files, but I also have it produce a PNG file, and then I uh, upload that using FTP to my website. So when you go onto my website and look at the real time display, that's what I'm doing there. And so you should be able to do that as well.
Yeah, I think that's something possible, and I think it would be kind of a cool thing to have on the website for sure. All right. Well, by the way, one more question for you. You recently had a bit of an earthquake off the Aleutians. I think that was about a couple of weeks ago or something like that. Any impact to you? Did you feel
No,
it?
none at all. Definitely saw it on my seismometer here in Anchorage, but didn't feel it at all. It was what, a 7.2
Yeah, seven
magnitude,
something.
and yeah, it was just south of Sand Point there in the Shumagon Islands, and I'm glad I wasn't there. I'm sure they headed to high ground, but I had not heard that there was any kind of a tsunami or anything that affected them. So a strong earthquake, but no tidal wave.
Well, we don't have to worry about that in Denver, at least yet.
You're lucky.
All
We
right.
get them here in Anchorage all the time.
All right. Well, yeah, I know Anchorage Bay is really, when I first got there, the first time I was there, I said, oh my God, if there's a big tidal wave coming in and focus right on the center of the bay at the end.
Well, it's so shallow that uh, like we had that 9.6 earthquake back in 1964. We didn't have any kind of wave action here in Anchorage at all, and because it's just so shallow, I guess that it couldn't propagate.
Probably true. All right. Well, you have yourself a great evening, and we'll see you this time next month.
Okay, sounds good then. See you guys.
Good
Thanks
to
a lot.
see you again, Whit.
Yeah, same here, Don.
Take care.
Thanks,
Yeah, you
guys.
too. See you
All
next
right.
month.
Good
Yep.
night.